Solar magnetic storms pose a disturbing threat to life on our planet. On the surface of the sun, a flare begins to boil, bubble, then explode.
It's a horrendous explosion on the surface of the sun, and you have this huge storm, a coronal mass ejection. These ionized particles fly away from the sun at extreme velocities.
These are unprecedented images from NASA's new satellite called SDO, the Solar Dynamics Observatory. Never before has humanity had such a close look at our home star.
The big difference between this observatory and previous observatories is that we're looking at all of the sun all of the time. Previously, we've looked at small areas, not the whole disk.
Launched in February of 2010, the SDO measures magnetism, ultraviolet rays, and even the interior of the sun. Already, SDO has returned never-before-seen close-ups of solar flares, magnetic rain, and tsunamis that ripple across the surface of the sun.
It's like having a DVR. You can go back and you can catch the interesting part, having an instant replay. So we're going to see the connections that we've never seen before.
One of the most important connections is that all solar activity is basically magnetic activity.
The key to understanding the variability of the sun is magnetism. We see sunspots, we see filaments, we see explosions, we see coronal mass ejections, big explosions of material into space. The only way to understand how that all ties together is through the magnetic field.
The sun's magnetism is created by the movement of superheated plasma as it ripples across the surface of our home star.
One of the ways in which magnetism is generated is by a moving current. So any flowing, moving charges will generate a magnetic field. The sun is one huge bag of flowing, moving charges.
One of the magnetic phenomena that can actually be seen from Earth is a sunspot.
Now, if you look at the sun and you see a sunspot, it looks like a dark spot. What's really happening is the magnetic field is twisted up on itself in a certain way. It looks kind of like when you pull the drain out of a bathtub and it spirals down into the drain. You create sort of a tornado, a vortex, on the surface of the sun. And you have extremely strong electromagnetic fields there.
A sunspot can lead to something far more dramatic, a solar flare.
There are explosions on the sun. We call them solar flares. Solar flares can be either fairly small, by which I mean the size of an atomic bomb, or they can be as big as 1 billion atomic bombs, all happening at the same time.
Solar flares arc millions of miles above the surface of the sun. These magnetic storms are more than simply intriguing astronomical data. The sun's magnetic field creates a dynamic, ever-changing atmosphere throughout the solar system. It has come to be called space weather.
Space weather is the idea that things that change in space can have effects on us here on the Earth. And how do we measure that? How do we learn to predict it?
Space weather can affect satellites surrounding Earth. High-powered X-rays from a solar flare can cause millions of dollars of damage in communications and navigation satellites. Astronauts on the shuttle and space station have to know the space weather forecasts to avoid deadly radiation during a spacewalk. These are the kinds of problems the Solar Dynamics Observatory is designed to predict.
Forecasting space weather is one of our big challenges. We want to learn how to do it better. Now, most of us don't really trust weather reports too much, a little bit, but not too much. We're way behind that. We're not anywhere close to being able to do that yet with space weather.